Da, 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 da. We are going to talk about simple harmonic motion. We are going to talk about simple harmonic motion. We are gonna talk so much about it. We are gonna talk about it. We are gonna talk about simple harmonic motion. Let's see if it recognized my handwriting, and it sort of did. Simple harmonic motion is something we will talk about. Yes. So yeah, simple harmonic motion, good times. This is Mr. Sameda talking about simple harmonic motion. The easiest example to think of is it's like it sounds, simple. So it's not going to be some sort of motion that changes. It's going to be harmonic, which just means it's going to repeat itself over and over. Okay? It's in harmony. It's going to be the same way. If I had two objects that were one next to the other, they would move exactly the same way. And the motion part, that's pretty easy. Okay. The easiest example is a mass on a spring. So here's our spring. We attach a mass to it. And we know what will happen if we do that. The mass will go down. It'll stretch out the spring. And then it will start to go back up. It'll go back to the spot where it started. Supposedly it's the same size block. And it will compress up here. And at this point, yep, it's headed down here. At this point, this is its maximum displacement. So this is, and this the top is v equals 0. And if we do this right, we'll end up with the same difference from here to here as we end up with from here to here. It doesn't really look like it did, but ideally that's what we would end up with. And the idea is pretty simple. We're going to look at those, and if we watched it at the very beginning, it would be at equilibrium. So it would be at equilibrium here. This is where it would sit. Here, the force of the spring is going to be more than mg. Here, it's at equilibrium again. And here, since we shrunk the spring, F of the spring is going to be less than mg. So we're going to end up with this thing moving up and down and up and down and up and down, back and forth, in supposedly with no friction, forever and ever and ever. Now, if I was to make a graph of, now, of course, it would be at its fastest point right here. And every time it got back there, even when it got to there, because that would be the point the two forces were equal, the acceleration would be 0. If we actually looked at the motion of it, like we made a graph of x as a function of time, we would start at well, I mean, if it was like this, we'd have to move it a little bit to actually get it to go. So we'd have to lift it up. And it would go like this. Again, it's not perfect, but you get the idea. That it's going to move up and down and up and down. Like this is if I moved it to the very top. Okay. So this is the equilibrium point. In the middle, the spring is neither stretched nor compressed. That's the length it would have if we just sat it there. And that point would happen here, and it would happen here, and here also. All of those are going to be equilibrium points. Now, if you look, we know that the slope of the line is going to tell us the velocity. So if you look, the velocity is going to be fastest here and here, here and here. The velocity is going to be fastest there. And in fact, you can see it's going to be negative here and positive here, negative here and positive there. Now, that's all we mean by that, is that it's going to be fastest there, fastest there, fastest here, fastest there. Ideally, it'll be the same both ways, so it'll go up and down. At the same, there'll be the same slope here as it is here, and the same slope here as there. The magnitude of all these should be roughly the same as well. If you look then where the velocity is 0 is here. I'm going to put a slash there to indicate 0. 0. I guess that's more the empty set or null, but we're okay. We're among physics-related friends here. All of these places have no velocity. These are the turnaround points, the points where it goes from one to the other, the top or the bottom. If I were to make a graph of velocity versus time, all these points would be my zeros. 0, 0, 0, 0, 0. This point here would be my negative maximum. So it's going to be down here. This is my positive maximum. It will be up here. This is my negative maximum. It will be down here. This is my positive maximum. I know I'm sort of repeating myself, but you get the idea. Okay. That the shape of this would be like this. Okay. And that's what it's going to be like. If you look at the velocity versus time graph, everywhere that the position graph is far from the position graph is far from the equilibrium point, like there or there. Okay, and those places are going to correspond to velocities of 0. And all the points where you're crossing the equilibrium are going to correspond to the points of greatest speed, whether negative or positive, depending on how the object is moving. Remember, here it's moving downward toward the bottom. That's why you have a negative velocity. And if you look, though, the period of this, the time it takes to get from here to here, is the same as the time it takes to get from here to here. So they're both going to move at the same frequency. The velocity is going to change at the same frequency that the position does. They won't behave differently. And while we're at it, let's talk about acceleration versus time. And the acceleration on a velocity versus time graph is represented by its slope. Slope is the lowest there. So we're going to have zeros here, 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 and here. But if you look, it's a negative slope over here, sloping down, so it's going to be a negative acceleration. This is sloping up. That's going to be a positive acceleration. And we're going to get a graph that's shaped like this. Now, if you notice, it's the exact opposite of the position graph. In other words, when the position is at its highest point, the acceleration is at its largest negative value, which, if you think about the spring, makes sense. If it's at its highest point, it's going to be lifted up. at that point, the spring isn't going to be given very much force. It's going to be given less, and most of the force is going to be downward from the force of gravity on the block. At the point where it's at the bottom, there's going to be a force trying to pull it back upward, and that force that pulls it back upward corresponds to the acceleration there. So this graph and this graph will always be exactly opposite, but you'll notice again they have exactly the same time period between cycles that this does. They're just in the opposite direction. So all the time periods, like the way that the position moves, the acceleration moves, the velocity moves, all of those time periods are going to be the same. In fact, if I represent this as a cosine graph, this would be best represented as a negative sine graph because it's going to go up and down. And this one would be a negative cosine graph. Now, how are those related is the trick. Well, there's a good video you need to watch right now. I want you to stop, and I want you to watch those 3 videos that are listed on this page as ones that you want for simple harmonic motion and circular motion. I just want you to watch what they look like so you can compare what happens when you look at simple harmonic motion and what happens when you look at circular motion. Oh, I don't think we want to go to instant search and whatever. So here we go.